Start off with some basic stuff in probability before we get into the diagnostic testing, which I think can get a little bit confusing. So maybe we'll kind of ease into that a little bit. On Blackboard, there's several files, including a couple of exercises that I put together, a couple of things we can do together, and so on. And we're going to just talk about just the idea of probability. I mean, it's the kind of thing we live with every day. You know, risk, probability. Some of us like to go to the track or gamble and stuff like that. We come across it there as well, or play cards. You know, like a game of pinochle or something like that. How many people here have ever played pinochle? No, nobody. Okay. Anybody know what pinochle is? No. Okay, there you go. Okay, good. All right, so let's go. Okay, let's see. I'm going to start with a simple exercise of sorts. Let me move this out of the way. And okay. You remember upstairs you were talking about independent events, you know, or events that were mutually exclusive. Okay, so you can have some events where they can occur again. For instance, if you have people that if you have people that are, you have a population of people, some of whom are insured, some of whom are not insured. If you pick a random person out of that population, they might be insured or they might not be insured. Pick another person out of that. They could also be insured or maybe they're not insured. Pick another person and so on and so forth. So those are independent events. We can randomly select them and they're each an independent event, but they're not mutually exclusive. You can get the same result if you tried it again. In other cases, for instance, if we roll a dice or something like that, uh, 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 there are only so many outcomes that are possible. For instance, if you flip a coin, there's only two possibilities, heads or tails. They're mutually exclusive. 50% of the time you'll get heads, 50% of the time you'll get tails. So let's talk about one of these kinds of events. Let's talk about the idea of a population like the United States, where maybe about 80% of the people in the population are insured. You're going to choose one person randomly from that population. What's the probability they're insured? Right? The prevalence is 80%, so it's 80%, right? Everybody okay with that?
Yeah.
Okay. You choose three people randomly from the population. One, two, three, completely randomly, right? What's the probability that all three are insured? Well, since they're independent events and they're not mutually exclusive, we use something called the multiplication rule, right? So if the probability of one being insured is 80%, probability of the second one being 80%, probability of the third is 80%, then what's the probability of all three of them being insured? 8.8 times 0.8 times 0.8. Put it in another, let's put it in another form. What's the probability that you'll flip a coin and toss three heads in a row? Well, what's the probability of getting the first head? It's 50%. Probability of getting second head is 50% and 50%. So 50% times 50% is 25%, right? Times 50% again is 12.5%, 0.125. Or 1/2 times 1/2 times 1/2. Well, that's going to be 1/8, 1/8, 0.125, same deal. Okay, so in that kind of situation, we can we can use a multiplication rule to predict what our probability is. Okay, but they have to be independent events. So, for instance, if I were to stand at the front of a church and ask people in groups of three entering, "Are you insured? Are you insured? Are you insured?" And I just took the next three people entering. Would that be independent events? Would those be three independent events? If I took them in sequence like that, one, two, three, the next three people entering, well, people tend to go to churches as a family, right? So if one person is insured, probably the whole family is insured. So that's not really an independent event. So it's really got to be a random sample, and it's got to be, and these have to be independent events for this to work properly. Okay, let's say you test 10 people, you choose 10 people randomly from the population. What's the probability all 10 are insured? 0.8 times 0.8 times 0.8 times 0.8 times 0.8, and so on and so forth. Okay, works for 2, works for 10, works for 100. Okay, now what's the probability that you chose 3 people and none of them are insured? Same population. Chose 3 people randomly. What's the probability that none of them are insured? Yeah, go ahead. Get
1 minus 0.8.
right. Now the probability they're not insured is 20%. Probability all 3 are not insured is 0.2 times 0.2 times 0.2. Okay? Not rocket science. It's really easier than it sounds, right? Okay. So, so we now I won't go into a little bit of that right now. So I'm going to take a look at. I'm going to open up this next exercise here, and I can represent this kind of thing using something called a probability tree. And what I'm going to do is I am going to open up a page here that we can see. And I'm going to draw this probability tree. I'm going to lay out these probabilities. And what I'm going to do here is I'm going to draw out all the possibilities for flipping 3 coins, the probability of getting heads or tails for each one of the outcomes of flipping 3. Tails. Okay. This is heads. First coin is heads. First coin is tails. I'll do it this way, 0.5. Heads, tails. All of these branches represent a 50% chance of the next thing occurring. So let's count up all the possible outcomes. Okay, so one outcome is let's see, heads, heads, heads. That's 0.5 times 0.5 times 0.5, which is 0.125, right? That's heads, 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 heads. Okay, and that's really what we calculated before, 0.5 times 0.5 times 0.5. Okay, what about heads, heads, tails? 0.5 times 0.5 times 0.5. The probability of getting heads, heads, tails is 0.125 also, right? All the probabilities are 25%, or 50%. What about heads, tails, heads? Heads, tails, heads, 0.125. What about heads, tails, tails? That's heads, 2 tails. That's 0.125. What about tails, heads, heads? Okay, that's going to be 0.125. Probability of getting tails, heads, tails. It's 0.125. And the probability of getting tails, tails, tails is 0.125. The same as it would have been to get, for us to get 3 heads in a row. 3 tails in a row, same likelihood of 3 tails in a row. Okay, so let's look at all these outcomes. It's simple enough to see what happened if the probability of getting 3 heads in a row or getting 3 tails in a row. It would have been 0.5 times 0.5 times 0.5 for each one of them. Well, what if I asked you what's the probability of getting 2 heads? Well, there's a lot more ways of getting 2 heads than there are of getting 3 heads or 3 tails. How many ways we have of getting 2 heads? Well, here's one. That's 2 heads. Here's another. That's 2 heads. Here's another. That's 2 heads. So there's 3 ways, each one of which has a probability of 0.125. So these are all mutually exclusive. This is one outcome, and all the outcomes put together are going to add up to what probability? One of these has to occur, so it's going to add up to a probability of 1. Okay, so in fact, if I add up 0.125 plus 0.125, it all adds up to 1. So Since these are all mutually exclusive, they add up to 1, I can figure out the probability of getting exactly 2 heads is going to be the probability of each possible way of doing it. And by adding them, I'll know what the overall possibility is. Okay, and that's the additive root. Okay, so let's see, 0.125, 0.125, and 0.125 is 0.375. Probability of getting 2 heads is 0.375. What's the probability of getting 2 tails? Right? Quick answer on that? Same thing, right? If you went back and looked at it, let's see how many ways can you get 2 tails? Here's one. I messed one up here. Here's one. There's 2 tails there. There's another place here where there should be 2 tails. Let's see here. Heads, tails, tails, head, tails. Here you go, that one over there. Okay, so there are 3 ways for that to occur as well. So we can kind of work this out manually using a probability tree, or we can use something we can examine this and we can do it a little bit more analytically. I'm just going to show you another possibility here. Let's take a look at this chart here. Okay, we have 3 multiple choice questions. Each one of them has options A through E. You guys have taken enough multiple choice questions in your lives. If you have no idea what the answer is, what's the probability of getting the answer right? 20%, right? Five answers. Probability of getting the answer correct is 20%. So if I were going to set up a probability tree for you guessing at 3 answers on a test, okay, it would look very much like that coin, except that in this case, the probability of it being correct versus incorrect is not 50%. Now it's 20% and 80% chance of getting wrong. Okay, so let's set up that tree right here. So we have the first question we have the chances of being correct are 0.2. Chances of us of being incorrect is 0.8. The chances of us on the second question being correct is also 0.2, and the second question being incorrect is 0.8. So we can have be correct and correct again, or we could be correct and incorrect. And then there's another 2 possibilities after that. We could be correct again, we could be incorrect on the correct answers, or we could be correct and incorrect. And each one of them carries with it the same probability. Okay, and you wind up with 8 mutually exclusive outcomes. Okay, and these 8 should add up to 1. These 8 possible outcomes should add up to 1. And in fact, let's take a look at them. So the probability we're going to get all 3 of them correct is 0.2 times 0.2 times 0.2, or 0.08. Probability that we're going to get them all wrong is 0.8 times 0.8 times 0.8, or a little over 50%, 0.51, right? A little disappointing, right? But I mean, if you don't know them at all, that's not too bad, right? So now what's the probability of getting 2 out of 3 correct, right? Well, there's a lot of ways that we can get that outcome. Okay, we can get that outcome by having correct, correct, incorrect, correct, incorrect, correct, incorrect, correct, correct, and so on and so forth. And we would add each one of those probabilities up to get the probability of getting 2 out of 3 correct, or 2 out of 3 incorrect, and so on. And these all that would add up to 1. Okay, so there's a lot of things that we can do with this. I want to show you, if I can find it, I'm going to show you a quick film. You might have noticed that if we look at this kind of as a distribution, that as we, with the coins, for instance, as we looked at this tree, the number of outcomes that if I had done it for 10 coins, the probability that there's only one outcome where I would get all 10 coins as heads. There's only one outcome where I would get all 10 coins as tails. But there's more ways for me to get 9 heads or 8 heads or 7. What do you think is the most common outcome, the most likely outcome if you flip 10 coins? It's going to be half heads and half tails, 5 heads and 5 tails. So that 50% outcome is going to be our most common outcome. That's what we're going to see most frequently. And in fact, we can kind of demonstrate this. I'm going to show you something. This is at the New York Hall of Science. Anybody ever been there? No, it's like in Queens here. It's part. I think originally the building was part of the World's Fair at one time. Okay, let's see if I can get this to play. Oh, okay, yeah. Here, now, let me describe to you what this machine is. You guys ever seen a pachinko machine? It's kind of like a pinball machine, except it's Japanese. You hit little levers and it throws a ball in the top, and the ball hits these pins and comes down in different patterns, and you get points for it and stuff like that. It's actually kind of a gambling machine in Japan. Well, this machine has a little dispenser at the top where it takes a ball, steel ball, it drops it down, and there's a pin directly underneath where the place where it drops it down. When it hits that pin, it can go either to the left of the pin or to the right of the pin. That pin's right in the center, so 50% of the time it's going to go to the left, 50% of the time it's going to go to the right. When it bounces off that pin, the next thing it encounters at the next level is two more pins that it hits and can go left or right. So it's analogous to this exercise that we just did with our tree with our probabilities for coins. Instead of heads or tails, it's left turns or right turns. So we would expect to see the lowest probability is that it would make all left turns and go all the way out to the left. And they collect in the bottom in little bins, so you can actually see them collect as this goes on. So I'm going to play this. Okay, there it is. See the coins? You see the little pellets dropping in there, and they can choose left or right, and so on and so forth. And as we pan back, you're going to start to see the result of this. See, some of them are going pretty far out, but then they turn back in again, and it's all pure chance, right? And then at the bottom, take a look at this, how they tend to distribute themselves. Pretty interesting, right? Okay. And there was at least five kids around here waiting for this to fill up so they could see it flush. At the end of it, it kind of flushes, and it makes a big noise, and they will go running at it. I think. But at any rate, you saw that interesting distribution. It actually represented physically this idea of how these probabilities distribute themselves. That happens to be something called a binomial distribution. We're going to be talking about that later on in the semester, but it's kind of interesting because it kind of ties into what we're looking at here. Okay, so let's move on from this and let's talk about applying some of this stuff to some of the stuff we did with diagnostic tests. Okay, so one of the things that we looked at in diagnostic tests is the way we laid out the data. We laid out the data in what we call crosstabs, in tables that have columns and rows, hence crosstabs. Okay, and we have titles, and the rows have titles, the columns have titles, and so on and so forth. This is a simple crosstab. This is a simple way of displaying data so that we can understand, what the numbers are, and so on and so forth. It happens to be the marital status of the U.S. population, 18 years and older. The numbers happen to be in millions. And I think this was, judging by the size of the total population, 214 million, this was probably like maybe in the 70s or something like that. Okay, I think we're pretty close up to 300 million now, or maybe over 300 million. But at any rate, so let's take a look at this. So we can see that we can see how many single people there are in the population, how many of them are male and female. These are numbers. They're not percentages, they're just numbers. Okay, so let's examine what this table can tell us. Number one, if a person is randomly selected from the population, right? In other words, we took all 214 million people. We picked one person out of the population randomly, however we would ever do that. What's the probability that that person is divorced? Well, how many people in the population are divorced? How many? 21 million, right? 21 million. How big is the population? 214 million. So the probability or the prevalence of divorce is 21.7 million over 214 million. Okay. What's the probability that that divorced person is male? Now it's 9 million out of two. Well, it depends on what the question is. If the question is, what's the probability a person is divorced and male, it would be 9 out of 214 million. If the question is, what's the probability that a divorced person is male, then It's 9 out of 21 million, right? So we got to be a little bit precise about this. What's the probability that the person is both male and a widower? Now, what we're starting to see here is some of the stuff that we were examining before using those Venn diagrams, the idea of unions and intersections and so on and so forth, but played out on this table, this organization of data. So what's the probability that that person is both male and a widower? How many people are males and widowers? 2.7 out of a population of 214 million, right? Okay. And that's the intersection of being male and being a widower. Okay. Given that the person is male, what's the probability that he's married? What kind of probability is that? Conditional, right? Okay, we're going to be working a lot with conditional probabilities. So in this case, we're saying to ourselves, given that the person's male, so we're only interested in the males, right? So what's the probability that male is married? 6 over 104 million. Okay, so now our first look at this idea of conditional probability. Okay, so we're going to take that forward a little bit. Oops, let me get this out of the way here. So we're going to move on to diagnostic testing. Okay, now this is kind of like a odd example that I put together. Let's see if I can even get this even a little bit bigger. Get this out of the way. Okay. Anybody here nickel sensitive? Have an allergy to nickel? Yeah, it's getting more common than it used to be because of medical implants and piercings and stuff like that. Because a lot of piercings have a lot of metal alloys have nickel in them and stuff like that. I know that like I have trouble wearing a wristwatch because the stainless steel back. If I get a cheap wristwatch, a lot of cheap backs have a lot of nickel in them, the stainless steel. And when I perspire, it dissolves a little bit of the back, and I wind up getting a rash from it. This is an Apple Watch. It has a glass back, believe it or not, because it's taking my pulse continuously. So, if I'm dead, it'll like make a beep. So at any rate, so at any rate, or whatever purpose that has anyway. So at any rate, so a lot of people are nickel sensitive. So it would be now a lot of times the way that you test for these sensitivities, you do these patch tests and so on and so forth. You do these challenge tests. Challenge tests can be a little bit dangerous, because like if you get someone that's really sensitive, you expose them to something they're allergic to, you can get a really bad reaction and so on and so forth. So allergies tests are really a kind of a special thing. But let's take a look at this. Let's say that someone has developed this much safer version of a test for a nickel allergy. Okay. Now he takes 100 subjects. Remember that little bogus kind of analysis for that Levi said that he was not comfortable with, where you took an artificial population. They take an artificial population. Now the manufacturer of the test wants to determine if it works. So he's going to take people that have a nickel allergy that he knows have a nickel sensitivity, and people that he knows don't have a nickel sensitivity, and he's going to try to test on both of them. So this is kind of our artificial population, but we're going to, after we find out the results of this, we're going to apply it to a real population. Okay, so let's take a look at what we do with our artificial population. We take a sample group of 100 subjects who are known to be sensitive to nickel, right? As it turns out, 80 of those people turn out to be, out of 100 people, turn out to get a positive test. Okay, so it identified, out of 100 people that have nickel sensitivity, it identified 80 of them correctly. So the sensitivity of this test is the percentage of people that it correctly identifies as positives, right? Okay, and when that comes out, what do we call those people? We call them true positives. In other words, they got a test, they got a positive result on a test, and indeed they have the condition, so they're true positives. Okay, the sensitivity is how good the test is at identifying those true positives. Okay, in this case, the test is the sensitivity of the test is 80%. Okay, now we take another control group. We want to know, well, that might be great, but what if it just tests everybody? 80% of all people positive, test isn't very useful. If it's testing also people that are not sensitive positive 80% of the time also, then the test is completely useless. Okay, so let's take a group of control subjects who are known to be not sensitive to it and test them. And as it turns out, 90 of these test subjects tested as negative. Okay, so now 90% of the time, it's correct at identifying people who don't have the sensitivity, don't have the disease. So that's called the sensitivity. Okay, so we have specificity is how good it is at identifying people that have the condition. Sensitivity is how good it is at identifying people who don't have the condition. Sensitivity, specificity. In this case, turns out that in this test the specificity is 90%. 90% it got right. Now, what is if that tells you that it correctly identified 100 people, identified 90 of them as not having a sensitivity to nickel? What about the other 10? What did it say about the other 10? It said that they were positive. They had nickel sensitivity, but they didn't. So what do we call those guys? In other words, guys, the 90 is true negatives. What are the other ones? They're false positives. They tested positive, but they don't have the disease, so they're false positives, right? People that test. We're going to get to that. We're going to get to the table. It'll be a little bit clearer. Okay. Okay. So let's take a look at this table. People who test positive and have the disease are true positives, right? Okay. People that test positive and do not have the disease are false positives. They tested positive, but they don't have the disease, so they're false positives. People who test negative but have the disease are false negatives. People who test negatives but don't have the disease and don't have the disease are true negatives. Okay, so if we look at this crosstab, this table for our diagnostic test, let's see what we have here. Okay, we have in the columns we have all the people that are sensitive to nickel that have the disease. We have in the next column all the people that are not sensitive to negative that don't have the disease, right? Now, what about in the row? In the rows, the top row is everybody that's positive, right? And that includes people well, everybody tested positive. That includes people that are indeed sensitive to nickel and people who tested positive that are not sensitive to nickel. The negative row, same thing. Get people that are not really negative, that tested negative, and people who are indeed negative. Okay, so now if I add all this up together here, down at the bottom, I get the total number of people who have the disease in that first column. That's the total number of people that actually have the disease. In the bottom of the second column, people who are not sensitive, I get the total number of people that don't have the disease. If I look across the row, if I add these numbers together, I get the total number of people that tested positive. Similarly, in the second row, total number of people that tested negative. Okay, any questions so far? Okay, let's move on. I'm going to make up a fake population. I'm going to tell you that this population is, and this is more of a simulated real population. I'm going to tell you that this population is the prevalence of nickel sensitivity in this population is 20%. You guys think the real population the real population prevalence of nickel sensitivity is 80%, 20%? Anybody think that's that high? No. What evidence did we just find here? What do we think? We got two people out of about 30, right? So that's probably closer to the real prevalence in the population. But I'm making up a fake population that has a relatively high prevalence of this condition. You know, there are populations in the United States, communities where the prevalence of diabetes might be 20%, right? Or other conditions might be 20. If you have an elderly population, among elderly men, the prevalence of enlarged prostates might be 80%, something like that, 60%. So you come across populations that have a high prevalence occasionally. So let's look at this one. Let's say that it's 20%. So if I were to make up a fake population and say that there's 1,000 people in this population, out of that 1,000 people, how many would have the disease if the prevalence is 20%? Right? 20% of the 1,000 people have the disease. How many people is that? 200, right? So that's why I put that 200 down there, right? That represents in that column all of the people out of the 1,000 that have nickel sensitivity. How many people don't have a nickel sensitivity? That'd be the 800. Okay? See how I'm constructing this table? Okay, so now, what did I say? How good was this test at identifying people that have nickel sensitivity? What was the sensitivity of this test?
80%.
It was 80%, right? So out of the 200 people that have a nickel sensitivity, how many people would I expect to identify with a positive test? Yeah, 160. 80% of them. How many people are going to test negative out of those 200? 40, right? There you go. There's your there's your true positives. There's your false negatives. They're false negatives because they tested negative or they have the disease. Okay, now specificity. Remember what specificity was? It's the probability that a person tests negative if he doesn't have the disease. So let's see. We have 800 people out of 1,000 that do not have the disease. The sensitivity of this test is 90%. A specificity of this test is, I even get it. I know how confusing this can be with these new terms. 90% specificity is going to be right 90% of the time identifying people that don't have the disease. So out of 800, how many people would it get right? 720. So where does that 720 go? It's in the lower right-hand corner, right? Because that's the number of people that test negative. Look at the intersection here. Test negative and are not sensitive. That's the right answer. What kind of test result is that? That's a true negative, right? Okay, good. Let's go back up to the top here. How many people are going to test positive in this population now? 80, right? Even though they're not nickel sensitive, 80 people, and that's what a test that's 90% accurate at screening people that are not sensitive. Okay, how many people tested positive total? Right, 240, right? 160 people that were true positives and 80 people who were false positives. We out of 1,000 people, we got 240 positive tests. How many people tested negative? Okay, 760. Okay, good. Okay, so now let's take a look at this. 240 people tested positive. How many people are out of those 240 who tested positive? How many of them actually have the condition? 160, right? So out of those 240 people, 160 actually have the disease. So the probability of having the disease, if you test positive, is 160 over 240, or about 67%, right? So our positive predictive value is 67%. Okay, so now we could have positive predictive value. The probability of A given that B has occurred. Whoops, where's the little pipe? There it is. Probability of A given that B has occurred. What is A in that? If I'm looking at this conditional probability, probability of A given that B has occurred is equal to 0.67. What's A and what's B there? Well, given that B has occurred, well, everybody in this group has what? Tested positive. Given that a person is tested positive, what's the probability, A, that they have the disease? So A is the probability of having the disease. What is that? That's the right probability of having the disease is the prevalence. And B is the probability of having tested positive. Okay, that's our positive. That's another way for us to express our positive predictive value. I'm just throwing that in here now because Bayes' law is going to come in handy to us at some point. It's going to be a little confusing, but it's going to come in handy. What's the negative? What do you think the negative predictive value? I'm going to scroll back down here. What's the negative predictive value going to be? What does negative predictive value mean? It means what's the probability of being negative given that you've tested negative? Okay, so how good is this at predicting that you are negative? Okay, so how many people tested negative? 760. Out of those, how many were really negative? 720. So what's the probability of being negative if you test negative? 720 over 760. Anyone want to figure that out? What is that? What does that come out to be? I've been ignoring the people online here. Let me see. How are you guys online doing? I hope you can still hear me and see me. And I don't see any questions in the chat box so far. So you guys doing okay? Okay, good. Okay, good. Excellent. Okay. So the negative predictive value is the probability of being negative if you test negative. It's analogous to the a negative. It's analogous to the positive predictive value. Okay, we could actually figure that out if you wanted to. I put it down here as I notated it as the test results. True positives over true positives plus false positives. In other words, the correct positives, the people that really have the disease and are tested positive over all the people that tested positive. Same thing with negative. People that really are negative that tested negative over all the people that tested negative. This is a negative predictive value. Okay, let's take a look at another version of this, except this time the prevalence of nickel sensitivity in the population is only 1%. We're going to apply exactly the same test. Okay, I'm going to give you guys a few minutes to do it. Okay, you guys fill out this table. Okay, you can do it. You can either look at it on the screen here. I'll blow it up even a little bit more. I want you to fill in all those boxes, assuming a population of 1,000. Okay, and except this time the prevalence is 1%. Same test, sensitivity is 80%, specificity is 90%. You guys having problems online? Now's a good time. You got my attention.